morning, everybody. So we just heard a little bit about quantum, what's going on in quantum by IBM in the United States. But today we're going to talk now about what's going on about quantum computing here in Barcelona. I'm Marta Estarellas. I'm the CEO of Qilimanjaro Quantum Tech, a full-stack quantum computing company based here in Barcelona that builds a novel way of doing quantum computation. And first of all, let's ask ourselves, why do we do this? So I'm, by training, a chemist. I used to work developing new drugs, new pharma, to cure diseases that nowadays do not have a cure. I was working with certain types of cancer, Parkinson, and Alzheimer, and that was my purpose. And the first step that we were doing in order to develop this new pharma was to try to cut down the amount of possibilities, which are infinite, and try to identify what were the most viable molecules that could inhibit some reactions, some harmful reactions that are associated to these diseases. And the first step to do this is not by doing clinical trials or experiments and so on. The first step to do this is by using computer modulation. So you embed the mathematics description of the molecule and the reaction, you map it into a supercomputer, and you study the viability of it. But the chemistry, the molecules, are described by a mathematics that is quantum. So the physics that we can see with our eyes, the microscopic world, is described by classical physics. But when we go to the microscopic level, what we cannot see with the eye, is described by the quantum mechanics. But the computers use a classical logic in order to describe the problems. So there was a mismatch. And for me, that was the spark in my brain that made me completely change my career. I moved into a PhD on physics, I moved into computer engineering, and I started to learn more about quantum computing and this revolutionary idea that you can use quantum mechanical systems to simulate nature that is intrinsically quantum. And this not only affects chemistry, this affects many other areas. The computing capabilities that we have nowadays are reaching their limits. We cannot keep the same pace of development of increasing the power of the processing units by keeping miniaturizing the chips. And the way forward to keep enhancing the computing resources, the computing power in a society that wants to be more and more digital every day is by making computers bigger. So we are racking CPUs, we are building data centers, data farms, supercomputing centers, and at a level where the number of data that needs to be processed, the capabilities that we need is so big that Google or Meta are announcing that they are building nuclear plants to power these systems. So that's the level of scalability, the problem of scalability that we have now in computing. So we really need to find better alternatives, more efficient and sustainable ways of doing computation in order to fulfill the demands of a society that wants more and more and more data processing, but also to be able to keep enhancing the understanding of the world surrounding us, to keep understanding nature, to keep understanding physics, chemistry, material science, astrophysics, by having the capacities of being able to simulate more and more and more complex problems. So this is why quantum computing comes as a very strong new hope for computing, for processing. Quantum computing, put in a very simple words, is the possibility of encoding data and information in systems that behave under the laws of quantum mechanics. And it's under these magic laws that we can distill some effects that, even though are very counterintuitive, such as the superposition, that you can have two states at the same, you can have two states simultaneously or several states simultaneously, or the entanglement, this intrinsic strong connection that you have with two quantum particles once they interact and you separate them apart. This magic phenomena is very powerful to be able to build a new logic of computation that for certain tasks is more efficient. For certain algorithms, we can do computation more efficient exploiting this logic. And what do we mean by efficient? It means either faster, so solving the problem is faster, takes less time. This allows us to be able to imagine resolving problems that nowadays are untreatable. So we don't have enough power, computing power, not enough time to be able to solve these problems. We can have better accuracies, because we don't have to rely on so many approximations to be able to reduce the complexity of the problem. We can reach the optimal solution and not suboptimals. And we have a way to do more sustainable computers, more sustainable processing, because the exponential speed up that the quantum computing might offer comes attached to a reduction of energy consumption. Actually, we are still trying to understand how this will affect consumption, but the first benchmarks indicates that it will reduce 7 orders of magnitude of energy consumption, which is huge. So it's very important. There's a lot of hope put in quantum computing. I already explained this a little bit. Data, information, is codified in ones and zeros, a very simple encoding. Images, sound, everything are bit strings of ones and zeros. Those are the basic unit of information that we understand now with classical machines, with classical computers and communication. In the quantum world, the basic unit of information is the qubit. The qubit can also be in the 0 or the 1 state, but it can also be on the 0 and the 1 state. This is what's called the superposition phenomena, and this only happens when you have a quantum mechanical system. It's very counterintuitive. So the light can be turned on and off at the same time. What happens that when you have 2 bits, classical bits, you can have 0, 0, 0, 1, 1, 0, or 1, 1. But when we have 2 qubits, you have more superpositions that are possible. You can have 0, 0, or 0, 1, or 1, 1, but you can also have 0, 0 plus 1, 1, 0, 0 plus 0, 1, or all the superpositions, 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And this is very powerful. And I like to put an example. This is not very rigorous, but I think it's quite intuitive in order to understand why this is powerful. Let's imagine how we would solve in the classical world the problem of the labyrinth that is in many newspapers. You have to start from the beginning and try to find the exit by doing trial by trial. You do it in a sequential way because you need to evaluate all the possible choices. With the encoding that superposition allows, with a quantum computer, you can, in one trial, evaluate all the possible choices at once. And that's the potential of quantum computing for certain applications. It's the exponential speedup or polynomial speedup that it might have on top of the energy reduction. And as mentioned before, this is not going to completely substitute classical computers. So quantum computers, I don't believe we are going to end up having them in the pocket. I don't believe that they are going to change the way we communicate nowadays with the phones, or the way we do computing at home, or we process images or text. I think they will be there to accelerate the resolution of certain tasks. And what are those tasks that might map very well into the capacities of a quantum computer? Problems that are intrinsically quantum. So nature is quantum by design. So when we go to the microscopic world, it's quantum, and it's the small things that build the large things that we can see and behave with classical mechanics. But if we go to the origin, to the base units, they behave under the laws of quantum mechanics. So we want to understand chemistry, we want to understand physics. It's a very good platform in order to map the description of this problem into the description of the quantum mechanical system that we can program. So we do a one-to-one mapping of the mathematics that describes the problem. So we do a direct simulation. Then there are other types of problems that are more common and more present in the day-to-day of the industries and our lives, which are optimization problems. Optimization problems is trying to find the best choice, the most efficient, the optimum solution of a problem that has many variables and many constraints. So for instance, how to more efficiently distribute packages in a large city, or how to better optimize an asset portfolio in finance by maximizing benefit and reducing risk, or even how to optimize the schedules of a hospital, that they have many shifts, many types of employees, and they have to have always everything covered. This is an optimization problem. And optimization problems, certain type of optimization problems that are very common, map very well to a mathematical description that can be embedded very well into a quantum computer in order to be able to reach the optimum. And then there's another thing that I really, really like, and I think is very promising, is AI. So we are putting out there a new computing paradigm, completely different to the way we do processing, the way we do computing, than what we are used with classical machines. So what happens if we reinvent how we do artificial intelligence based on this new logic that we are putting out there? What happens if we unify quantum with AI? One of the big issues that we are seeing with the boom, with the AI revolution, with this boom, that everybody's using AI nowadays, and it's getting introduced into the production pipelines of many companies, but also in our day-to-day. This AI, these models that need to be constantly retrained, that demand a lot of data processing. One of the big limitations that they have is that they consume a lot of resources. So what happens if we find a way with a quantum computer to compress these requirements, to compress these resources into something that is more efficient? So I think there's a lot of promise into that direction, but it's a very new field. And then this is not precisely an application, but it's an important point of quantum computing. And there's now a lot of interest from the different continents, from the different countries, to protect this technology. This technology, in the same way that has a lot of power and potential to bring good and keep advancing the development of new technologies and understanding of the world and become more and more efficient as a society, it can also do bad. So one of the big threats of quantum computing is the possibility of breaking cryptographic keys. There's an algorithm that's called Shor's algorithm that what does is to solve the factoring problem, which is very much attached to the way we encode data into many cryptographic encodings. So a quantum computer could have the potential to break that. So that's why there's also a lot of protectionism and threat around quantum computing. But I always like to think about it from the positive side. Any technology can be used for bad and for good. It's our responsibility and our ethics to make sure that it's always being used for good. And what is the situation right now? There's a lot of hype. There's a lot of hype around quantum computing, in the same way that there's a lot of hype around AI, metaverse, and any new technology that comes out. And we need to be responsible and we need to be careful, because it's a very powerful technology, but it will take some time until it reaches the full matureness to be able to provide widespread advantage to the different industries and the society. But we are doing well. There's a lot of startups. There's a lot of big giants, big technological giants supporting the development of this technology, like IBM or like Google. And there's a lot of initiatives. There's a lot of wide search of the right technology, the right way of building a quantum computer. And there's a lot of collaboration, which I think is crucial at this point of development. Why do I say that this is still a little bit immature? Because there's still not a defined hardware platform where we will encode these systems. There's still not a defined type of qubit, which is the basic unit where to encode the quantum information. There's still not a defined type of quantum computer. There are many options being explored. So in this axis, what you can see is the different types of hardware platforms that are being proposed and are being investigated. So we can encode information into atoms. We can encode information into degrees of freedom, into light, into photons. We can encode information into semiconductor transistors, or we can encode information into superconductor circuits. And as you can see, a lot of focus is put into superconducting. And we are also putting focus in superconducting because at this point, so far, it's been the most scalable quantum hardware platform and the most controllable one. even though the other ones are advancing as well very rapidly. But then there's another variety. So how do we encode the problem? In the same way that in the classical world, we have the coexistence of analog and digital processing. In quantum, we also have the analog and digital processing. In the digital processing, what you do is to encode your problem into a circuit, into a sequence of definite, of finite gates that mediate a logical operation into your system. In the analog, what you're doing is to encode in the problem into a continuous parameterization and slow parameterization of your chip parameters. Different ways of doing computation. At the end of the day, you start from an initial state and end to a final state, which is your solution. And how you get there, it doesn't matter. They have different implications. But at the moment, they have a strong difference. And as you could see before, most of the approaches are focusing on digital. We are just one of the few that are focusing on analog. But why are we focusing on analog? It does make a lot of sense to start with the digital. Me, myself, when I started in the field, I started working many years on the digital quantum paradigm, because it's very neat. It's very smart. It makes sense. You encode the problem into a set of gates, a definite set of gates, and you can completely program in a universal manner any problem that you have. It's the same way that we process information with CPUs. But there's a problem. It's that quantum mechanics, quantum computing, quantum information is very sensitive to errors. And every time we apply one of these gates, we are introducing an additional error, because these gates are still very faulty. Not very faulty, but a small error on one gate that gets carried on, gets added and accumulated, and at the end of the circuit, at the end of the computation, the error is so big that it's difficult to make sense out of it. So we need to be able to correct for these errors. And there's one way of doing so. It's called error correction protocols. But these error correction protocols, because quantum mechanics is a bit tricky, demands for a lot of redundancy, demands for a lot of qubits, demands for encoding logical units of information into many physical units. And that means large chips. At the moment, we are at the point where the digital chips are of the size of hundreds, thousands qubits. But if we want to be able to encode larger, if we want to be able to encode error correction, we need much larger chips of the order of millions. So we really can keep pushing this, which I think we should, but it will still take some time until we are able to scale the hardware up to the point where we can implement these error correction protocols to make quantum computing useful. So it's also worth trying to find alternatives. And there are some alternatives. And we are following one of them, which is this alternative path to quantum computing via analog processing. Why do we do this? Because the analog processing, because of the way you control the system, the way you encode the problem, is less error-prone. It's more tolerant to the errors that you might introduce from the control. But also, we have a different idea on how to approach quantum computing at the beginning. So that in Spain, we say you don't start the house from the roof. You start from the base, and then you start building up. We don't think that starting to build universal platforms might bring the benefit of quantum computing in the shorter time frame. We think that first we need to focus on an application or the family of applications, and then we will open the tunability. So let's try to focus first on app-specific systems. And then the other one is coherence. So we focus a lot on building chips that are coherent. This means that do have a long time of protection of the quantum effects. Coherence is basically the time that you can guarantee that your system behaves quantum mechanically, and therefore you have quantum effects, and therefore you can harness some quantum advantage. And I like to explain a little bit why do we think that analog and app-specific might also come first, and it's also learning from the history of computing per se. The first computers in the 1940s, 40s that were occupying big rooms were actually app-specific. They were solving a specific problem that was out there. And they were analog, the first ones. Then we moved to digital. Now we are starting to see analog again for AI training, but they coexisted and they keep coexisting as for certain applications. And what do we do as a product? We develop a full stack. So nowadays, quantum computing there are not that many companies pursuing it. So if you really want to be efficient, if you really want to approximate as much as possible the design and the fabrication of the chip to the specific use case that you are trying to solve in order to identify this clear application to provide quantum advantage, you need to do everything. It's a bit crazy, but it's the truth. So we develop everything from the access layer to the algorithm portfolio, programming framework, the language that you need to program, the operative system, you need to reinvent the operative system that you use to control these systems, all the way down to the design and the fabrication of the chips, which is where our big IP and our differentiation relies on the type of chips that we do. And what do we do with this? We want to democratize the technology now. It's ready to provide advantage? No. It's not. But we think that it's very important that this technology is out there, such that engineers, programmers, researchers, universities, governments, research centers have access to it and start learning how to use it. Because the worst that can happen is a technology that comes, that is very powerful, and we don't understand. And quantum is difficult to understand. It's difficult to program. We need to make a complete mind shift in the way we imagine algorithms, in the way we imagine computation. So we think it's important to create open access, to provide the technology to all these stakeholders to make sure they can start speaking quantum. And we are going to open the first quantum data center here in Barcelona, providing this widespread access via cloud solution. On top of that, we are partnering with HPC centers and governments and research institutions to be deploying quantum computers in premise for them, because they also want to do the same exercise. They want to make sure that their users have access to these platforms, that the users are learning how to use quantum. But what are the problems that we can tackle? And you will see that I introduced at the beginning a little bit what are the applications that seem to be more suitable for a quantum computer. If you remember simulation of physical systems and chemical systems, optimization, and AI. And we are starting to explore with different companies, with different sectors, what are the use cases, what are the pain points that they have, what are these hard, complex problems that would make sense to translate into a quantum computer. And we realize that there are so many. Every single industry that we spoke with have a problem that can be mapped into a quantum computer, and that it will make a big advantage for them to solve in a more efficient way. In logistics, I mentioned the last mile delivery dispatching systems, how to distribute packages in a large city. Retail, we work with retail on warehouse optimization, so very large warehouses that needs to be optimized. How the different autonomous robots that are inside the warehouse goes to pick the packages and how they move around the space. That's an optimization problem. Drone routing. Day-ahead price market, we had the big apagón a few weeks ago, and it's very related to the way, well, we don't know what happened, but I think it's very related to the way we optimize the energy market in a specific country by getting the information from the flows, the demand, the different sources of energy. And this is an optimization problem that is being solved by an algorithm that's called euphemia, that is very, very complex. And we managed to map euphemia into a quantum algorithm that would solve it more efficiently. Operating room resource optimization. This one was a surprise for me, but apparently hospitals have very hard optimization problems in their chirurgical rooms. Telecoms, commercial optimization, why people leave or wants to change a provider, a telecom provider. That's something that is an optimization problem. Green hydrogen production, simulation. Cybersecurity for critical infrastructure protection, that's also very important nowadays, how we protect our infrastructure from cybersecurity attacks. find and index tracking, emergency medical drone dispatch, how we optimize the electrical system in railways, or how we optimize our telecom networks. Those are just examples of the many problems that we have. We also collaborate with CERN in understanding the events that they observe from their detectors for the Atlas project or the Hyperkamiokande project for neutrino detection. They get many images, and they don't have the resources to process. So what we are studying is whether we can encode it into a quantum AI algorithm to be more efficient with the resources in order to identify what they are observing in those macro experiments. But even though there's a lot of potential, I want to emphasize there's still a long road ahead in order to develop this technology. And we need to be very rigorous with it. We need to make sure people understand, and we don't need to deceive anybody. So it's very promising. It's going to come, I'm very sure, but it will take some time. And we need to go step by step. We need to walk before we can run. But let me show you a little bit how a quantum computer looks. Let me show you this video, how here our team in Qilimanjaro built one of the first quantum computers in Spain that is now providing service to the entire national network of supercomputing users in order to learn how to speak quantum. You will see that this is not a typical computer. This is actually a very complex engineering system that sometimes we see them as a very black box, but this is the insides of it. They have to be at very low temperatures in order to be controlled. They are very bulky. They need to have a lot of complex engineering devices to keep the temperatures down, to make sure that the cabling is being communicating the pulses into the chip, and so on. So as you can see, here is where you put the chip. This is the cryogenic unit. The cabling goes all the way down in order to be able to control the chip. This has to be cooled down to around 0 millikelvin, so almost absolute zero in order to be working. This is an example of the chip. And anyway, that's a little bit it. That's the idea. This is still complex and very niche technology that there's a lot of interest to make sure that it gets evolved. And it's very, very important for us that we don't do this path, this road alone, that we work along with the final users to make sure we direct the solution to something that it makes sense, to something that can provide advantage and the revolutionary impact that we expect this technology will have for the society. Thank you very much for your attention.